for me, it's important that we understand something that is very fundamental when we talk about science in general. And is that there is a need of giving more space to the younger generation. I already have my beard white, and so I think, I have done what I had to do. So we need to wait for fresh minds and fresh ideas and visions, and that's why I decided to actually invite Robin, our paraprofessional at Colorado College, to give this talk. Robin has been student here at Colorado College. graduated last year. And even though at a young age, she was into many, she is and she was in many internship and fellowships. And one of which was in 2018 and was an internship to go study abroad. And Robin, if I understood, you decided to go to New Zealand. There you did a lot of work with professors and students there at the University of Canterbury in New Zealand. And your research has focused and touched also on volcanic topics, especially regarding the Whakaari volcano that is known also as the White Island volcano, that I have also been honored to publish a little bit of. And it is important to also say that that Robin has been coming back to the publication, but it is also like important to mention that Robin has been like very active in terms of community-wise, because she was part of the team of the lacrosse here at Colorado College for 3 years, playing the 3rd division now, I know. And you have done a lot of games, but that didn't prevent you to have very satisfactory results. And especially about this experience that brought you to publish an article that I also posted on the email about altered basalt ballistics from the White Island Whakaari volcano. And this paper was included a lot of collaborative research, a lot of students, faculties. They're mentioning Ben Kennedy. And we will see next also another presentation by a PhD student at Canterbury talking about the science, communication, and virtual field trips. So, but with no further say, now Robin, is your turn. And the title of your talk is A Multidimensional Research Experience with Hydrothermally Altered Ballistic from the Conduit of Whakaari Volcano, New Zealand, by Robin Hilderman. Thank you.
Thank you, Rosario, for that really wonderful introduction. And yes, as you've already mentioned the title of my presentation, I'm just going to jump right in. Let's see. Okay, so first I want to make some acknowledgements to Dr. Ben Kennedy for advising me through this research, as well as Dr. Marlene Villanova and Dr. Stan Mordensky. Both were really crucial to introducing me to a lot of the methods I did to conduct this research, as well as just being patient and talking me through it all. I also want to thank the geology department at UC for allowing me to use their facilities. I did break one thing, there was no effect from that, so that was appreciated. I also want to thank the geology department here at CC for funding my trip to GSA in 2019 to present this research, and I also want to thank Dr. Rosario Esposito for inviting me to give this talk. Okay. So to give a little geologic background on White Island, or Whakaari, which is the Maori name for the volcano. On the right, you can see this image of it from a reconnaissance mission by Heap et al. In 2016. Those are actually Ben Kennedy's shoes that he's dangling his feet out of a volcano. They're not to scale, but Whakaari emerges from the Pacific Ocean about 48 kilometers off the Bay of Plenty on the North Island of New Zealand. You can see in that photo on the left. And it is about a 300-meter andesitic stratocone, and its magmatism is the product of oblique western subduction of the Pacific plate under the Australian plate. And it is currently one of New Zealand's most active volcanoes. And the volcanic activity is modulated by a variably permeable hydrothermal system and surface hydrology. And so the objective of my research was to acquire experimentally derived permeability data to compare with other andesitic volcanoes such as Mount Ruapehu, which is in New Zealand as well, and to kind of understand and highlight the influences of hydrothermal alteration, fractures, and confining pressure on permeability. Okay, so the samples that I looked at are hydrothermally altered ballistic blocks erupted from a phaneritic eruption in 2016 of April. And you can see those blocks on the left are what they look like, and that there are varying levels of hydrothermal alteration from the core to the outside. And they were actually gathered by a previous CC student about 2 years above me. His name is Aaron Farquhar, who did the same study abroad program, and his kind of research project that you do for one of the courses took a more mineralogic and petrologic investigation to understand these blocks, where mine was a bit more permeability and rock mechanics side. So the cores that you see on the right, Aaron had already made, and there were 4 that I looked at that I then cut in half with all varying levels of hydrothermal alteration. And then induced a through-going tensile microfracture by the Brazilian indirect tensile test using a uniaxial compression frame, also called a CMT. And so the photos A, B, C, and D are immediately what the cores look like after that induced fracture. And then there have been previous permeability studies on ballistics from Whakaari to understand the behavior and evolution of the hydrothermal system of the island. However, none of them included decreasing confining pressure. So that was a focus of my work. And so there are 2 sets of permeability measurements that I made. The first, so of those 4 cores cut in half, so 8, they were loaded into a hook cell, which is kind of just this like kind of big rubber red sleeve that was put and connected into the CMT and had a steady state gas permeameter connected to nitrogen gas, which would flow that gas through the cores. And they dwelled at 1 megapascal for 30 minutes. And then the next set of permeability measurements, we looked at 2 end members of hydrothermal alteration and manipulated the confining pressure to mimic the environment of the increasing depth of the conduit of Whakaari. So of those 2 end members, one of them you see in this photo on the right, the purple core. So that has less hydrothermal alteration than the other one that we studied. And they went through the same process. However, they experienced an increase and decrease in that confining pressure. So from 1 to 30 MPa, increasing in increments of 5 and then back down to 1. Okay. So the results. So these 2 figures are using connected porosity measurements of these cores that was already acquired from previous studies and are plotted on a log linear axis. And so my measurements are the permeability. And so the figure on the left is pretty much just showing that those bottom dots below the arrows were the permeability measurements before a fracture was induced, and then after. And so there was an increase in permeability, which makes sense. You have more void space, more gas is going to be able to travel through those cores. And then just highlighting how a fracture increases permeability on the right. all those other points of data are from other studies of rocks from Whakaari, and just again highlighting that a fracture increases the permeability. Okay. And then these next two diagrams, we're starting to investigate the relationship between changing the confining pressure and hydrothermal alteration of these samples, and everything, all these measurements, the cores have already been fractured. So the one on the left, you see that with that increase in confining pressure, so toward the right, the orange and red samples have a decrease in permeability. And so as the cores are kind of tightened, those void spaces and fracture that we induced close, which makes sense. And what's important to note is that there's a larger change, a larger decrease in permeability compared to the unaltered lava, that those block squares, the black squares. So more alteration increases a larger change and decrease in permeability. And then the figure on the right actually has that same data of those red and orange dots, but they then also show the decrease in confining pressure. So you kind of read it left to right, going from about that, about 10 to negative 12 down to the very bottom on the right, and then kind of back up to about 10 to the negative 13 and a half. And so here we see an inverse relationship between the permeability and the confining pressure. So as the confining pressure increases, going from 1 to 30, the permeability decreases. And then going from 30 to 1, we see the confining pressure, the permeability increases. However, what's interesting is that it does not increase back to its original permeability at 1 MPa that it experienced before that cyclic change. And so there is some permanent damage that these cores have from that cyclic change of permeability. And so from these measurements, that deformation of the micro structures with increasing pressure show there is some impediment of the flow of gas within these cores, causing non-reversible damage. And yeah, it cannot be, you cannot bring back the original permeability that it once was at. Okay, and so following the completion of that, I actually did another kind of cycle of increasing and decreasing confining pressure permeability measurements on those two cores. However, they really kind of just failed and lost their structural integrity and really clogged up the machine. And so I was unable to kind of gather any data from that, but that was important to note. But besides that, so at the end of this class that I did this research for, I presented this poster there, but then it also was invited to present at GSA in Phoenix in 2019. So this is a photo of me at the poster session. And it was a really great experience to kind of stand next to my work and feel confident in what I'd found and explain it to anyone who was interested to hear about it. I also took advantage of the opportunity to go to the graduate school booths that were around and kind of start to understand what kind of programs they had there. I did not stay for the whole length of the GSA. I was in said strat, and so I had to be in and out of there about 24 hours to make it back to class the next day. But I still enjoyed it. I got to stay in an Airbnb with my friends from abroad, so that was just nice to see them. And then on to the publication. So it was kind of always discussed that some of this work would be incorporated with other data that has been kind of like compiling about Whakaari. And so this paper kind of provides a comprehensive insight into the conduit processes and to better understand the evolution of the hydrothermal system of Whakaari, including more mineralogic and petrologic findings and other rock property findings. And so this is kind of the money diagram, you could say, from the paper. So yeah, the photo on the left shows a bit more of the kind of mineralogy that occurs in the hydrothermal system, as well as more of the structures that the edifice and the conduit have itself. So my contributions to the paper kind of supported the already observed relationship that permeability and altered fractured conduit and the altered fractured conduits, so kind of where there are fractures in these images, are more confining pressure dependent than the surrounding less fractured unaltered edifice, and that this has an implication that the cyclic deformation, so that increasing and decreasing change in confining pressure, can result in a tendency of reduced outgassing and increase the likelihood of a more explosive eruption. And I will be honest, my contributions in terms of editing the publication during that process were really none. I was definitely offered to contribute to edit. However, I did kind of feel that I just kind of lack experience compared to the other authors. But now moving forward in the future, I definitely will be more confident in my knowledge and experience, and do want to partake in that because I know that's part of, being in science and writing research. Yeah. And those are the resources, and I just love this photo. So just